Hi, Mick McQuaid here for iste782 Visual Analytics. And today I'd like to mostly talk about mostly about Chapter 8, a little bit about Chapter 7 also. So this is from our textbook, R for Data Science, Part 2. So let's get started. So our textbook turns to getting data in and getting it into a usable form. And the chapters may seem a little out of order, first telling us the form in which to put the data, then talking about importing data into that form, then talking about transforming the entered data. So it'll seem like we're skipping around a little at first. And I should preface this by saying that I don't start out when I'm getting data into R. I don't use R at first. I just use Unix utilities. So here's an example. This is an example of a Unix pipe. The top line, that is, everything else is the output from that command. So the command is divided into 4 parts that are separated by the green vertical bars, which are called pipes. And this data is the H1B data set, which I think comes from a Kaggle competition. It's successful and unsuccessful H1B applications over the past few years. So what I've done here is use the cut command. This is a Unix utility. This is available. All these utilities are available on all Unix, Linux, Mac OS machines by default. And then you can also get them on Windows by adding packages. So first I have the cut command. That goes all the way over to the first green bar. So it says cut-f3-d, comma, and then the name of the file. The -f is which which field I want to, I was going to say column, but which field I want to cut from the file. So cut is column oriented. And I've chosen to cut the third field or the third column. -d stands for delimiter, and that's the delimiter between columns. In this case, it's a comma because it's a comma-separated values file. And the name of the file is h1b.csv. The pipe character means to take the output of the command on its left and use that as the input for the command on its right. So the command on its right is sort-n, so that sorts the results of the first command numerically. So the first command gives us all the years, 2017, 16, 15, 14, 13, 12, 11, and also the header for that column, which is case submitted year. And so it sorts those numerically. Then it passes off that output to the unique command. The unique command records how many copies there are. The unique-c command, I should say, records the number of copies of each unique value in the column. So that's what gives us the result below. And then that's passed off to sort-nr, that's sort numerically and in reverse order. So that's what gives us the final output of the number of H1B cases processed in each of the following years. And you can see that there's a decreasing number for each preceding year in the data set. And then the very last entry is the header of the column, which is case submitted year. So this is the year in which the H1B case was submitted that was either approved or rejected. And I can use this cut command on any of the columns in the file. So for example, another column I might be interested in is the number of cases approved versus number rejected. I can find out what the proportions are there quite easily using this command. And I can also find out if there's malformed data. So it's very often the case in CSV files that the data is malformed, by which I mean that there are extra commas in addition to the commas meant to delimit the columns. And so I can find out, if there are columns that will be read in by R that are unintentional, and I can easily find the source of those by using some other Unix commands. So I do a lot of this stuff just at the Unix command line, and in fact there is a recent O'Reilly book that you might want to look at called, I think it's called Data Science at the Command Line, which talks about how to use these kinds of utilities in more detail. Let me just give you one other example. I usually don't like CSV files because they're often badly formed. So I like to convert them into TSV files because I find that most files don't have tabs in them. This first command, grep tab h1b.csv, is intended to find out whether or not there are any tabs in the file. If there aren't any, then it makes a good candidate for converting into tab separated values format. The second line here, the perl-pe, is a command to change all the commas to tabs in the h1b CSV file and send the output to a file called h1b.tsv. So, and the idiom here, let me just highlight this idiom, that the Perl command uses is very common. It's not just Perl, it's used in a lot of utilities and languages. So this is S for substitute. The slashes, there are 3 slashes here, and they delimit what it is that I want to substitute and what it is I want to substitute it with. And this is literal. This isn't, I don't type out the letters C, T, R, L, etc. What I do is press Control V, and that tells the system that the next character I want quoted rather than acted upon. So that means I can then press the tab key. So I don't type out angle brackets and tab. I actually press the tab key after I press Control V, and that makes tab be the replacement pattern rather than having the tab actually act as it normally would. And then after the slash, I can put modifiers to the command. This modifier is G for global. That means to do this to all the commas in the file, not just the first one that it encounters. If I don't put G, it'll just modify the first comma that it encounters. And these are redirection symbols. This directs the input to come from this file. The input for this command comes from this file, and the output of this command goes to this file. And this is also a very common construction. You'll see this a lot in command line utilities. So, and the Perl-P, this -P stands for print every line, and the E stands for what comes next is a Perl program. So this is actually, believe it or not, a complete Perl program on its own. It just says to do a substitution on every line of input that it encounters, and the input is coming from this file. And I may need some additional manipulation depending on CSV style. The CSV style in this particular file was easy to cope with, but it's very often the case that there are double quotes in addition to commas to allow you to include commas in the input. And that doesn't always work correctly, but it often happens. So you may have to do additional manipulation. I frequently, if I have to deal with CSV files, will use a tool called CSV Kit, which is very good at uncovering irregularities in CSV files. This is a really common problem in data science, is that so much material comes in CSV format, and it's not a good format. There are much better formats, but they're just not used. CSV is definitely the standard, and so you have to get used to trying to work with it. Okay, now the goal state for what we're going to be entering in is a tibble. And the tibble is described in Chapter 7. It's a data frame. It's an R data frame, but it has some refinements to it to make it easier to work with. So if you have a regular R data frame like the iris data, this is a classic data set. Anybody who does data science should just sort of automatically know about this data set. If you have never encountered it, I will look at you funny. You should have encountered this somewhere along the line. it's descriptions of some irises that was a famous experiment long ago. Anyway, this data frame can be converted into a tibble with the as_tibble function. And so you see that the format of the tibble is the way it's presented, the way that it's printed is very nice. It shows us the types of the different data. So this column is all doubles, this column is all doubles, this column is factors. And these are the names of the columns. And it only shows us an amount that fits on our screen, or in some cases, a little less than that. Okay, and we can create a tibble on the fly. So here's a command that makes a tibble. This is the first column, x 1 through 5. That's this column right here when it's printed out. Y equals 1 is going to cause as many 1s as there are values in this column. So that's this column of 1s. Z is x squared plus y. So you can see that this is just a result column computed from these two columns. So we're interested in using this particular kind of data frame. Oh, and let me go back to this one. Let me also mention that this has shown us that x is an int, and y is a double, and z is a double. This is also creating a tibble. So even though it says tribble, that tribble just means create a row-wise tibble. So instead of creating column 1 here, and column 2 here, and column 3 here, we create row 1 here, row 2 here, and row 3 here, and this is just comment to make it easier to read. So a tibble is a data frame. It behaves a little bit differently from other data frames, but it's still a data frame. So here's a data frame created by X being randomly generated from a uniform distribution, and Y being randomly generated from a normal distribution. So there are 5 observations in each, and I've said options digits 2. Why am I getting 3? I can't remember what the issue is with that. In any event, if I then say $df$x, here's what's in that column. If I say df bracket quote x quote, I get exactly the same thing. And if I want to extract by position, the first column, this is a reference to the first column. So it prints differently and subsets a little bit differently from a data frame. But you can make it behave as a data frame. So if I then take df, this was the tibble you might recall from the last slide, and say create it as, say, convert it to a data frame, and then I inquire of it what its class is. Its class is data frame. Okay, so now on to chapter 8, which is about reading with the readr package. So when you say library tidyverse, it's going to import the readr package as well. And it contains functions like read CSV files, read tab separated values files, read delimited files, with any delimiter, and read fixed width field files, fixed width files or fixed width field files. I can't remember what. But in any event, a lot of scientific data comes in formats where the columns are of fixed width. So that's useful for that. Okay, so here's an example of reading CSV data. And when you use this function, So this is a little bit different from R's built-in read.csv function. This tells us what each column has been parsed as. So this is just the same thing as the built-in auto data set. It's just been saved as a CSV and then read back in. And you can see that this is double, this is integer, double, horsepower is character for some reason, and so on. And we'll talk more about why it chooses those things in a minute. Okay, now you can also read in tables that are created inline, and this is good for reproducible research. So it's very often the case that you'll get some R code and it'll make reference to a table or a file or something that you don't have access to. You know, the code becomes separated from the data. So that's really a drag. So it's really nice if you can create inline tables so that you don't run into this problem of files getting separated from each other. And you can include if you are using files, or for that matter, if you're using metadata, if you're using inline tables, you can skip metadata. You can include metadata in the specification and then skip over it. So it's a way of documenting the data. And you could also skip comment lines. So this works both with inline data or data in files. It's very often the case that CSV files don't have header lines. So you may want to say that column names are false in your invocation and that all you're importing is data. And in that case, R gives it default names, gives the columns default names. You can also read in files or do inline data that uses other characters for NA instead of NA. So a typical thing for a not available piece of data is to put a dot in its place. And so you can just say NA equals dot, and then when it's read into R, you'll get back NA. readr has a number of functions that together make an informed guess about the contents of a file that you try to read into a tibble. And understanding these functions can help you wrangle data into a format that R can work with. Now you can always go back. You don't have to understand this. You could always just go back and coerce data into the format that you want. But it's better if you understand. You can work faster and more effectively if you understand. So you have to look at how readr parses vectors or columns of characters. So it has 8 functions for doing this. Parse logical is one, parse integer is one, parse date is one. See, what's happening here is parse logical is parsing these values as booleans. Integer is parsing these values as integers. Date is parsing these values as dates. Double is parsing these as doubles. And notice that although in the US we use the dot as a decimal mark, in other places in the world the decimal mark is a comma. So you can change the locale so you can read in. And you can actually change the locale so that you would get a comma here too if you want. You can change the locale for your output separately. I'm not going to do that. I'm going to stick with US output, but my input may be from a different country and a different locale. Notice what parse number does here. So parse number ignores characters that surround numbers, ignores non-numeric characters. So it's ignored the $sign here, it's ignored the %sign here, it's ignored the words and the $sign and the dot here. And it ignores grouping characters. So parse number ignores grouping characters. So in the US, we often use commas as grouping characters for in in numbers, in integers, and by the way, this doesn't affect how it's stored. This is using a different locales grouping mark, using the dot as the grouping mark in the same locales that use the comma as the decimal mark. This, by the way, I should mention, this is just scientific notation, so this is, in case you're not familiar with it, this means times 10 to the 8th. It's equivalent to saying 1.23 times 10 to the 8th power. Now, a string is more or less a series of hexadecimal digits, and we're going to treat it as if it were a series of hexadecimal digits. If you read up on Unicode, you'll find that it's a little bit more complicated than that, but we're going to ignore that complexity here. We can afford to, for the most part. The mapping between a pair of hex digits and a character is called the encoding. So here's the actual word encoding changed to its raw format, so it's pairs of hexadecimal digits. And readr uses an encoding called UTF-8, but incoming text may use a different encoding. So we have to be aware of that. We have to be able to work with different kinds of encoding. So here's an example of a string that's difficult to read in because of this. So the encoding here is called Latin 1, which is also known as ISO 8859-1. That's the same thing as Latin 1 encoding. And if we parse it as if it were, the UTF-8 result of that is going to be El Nino. So we get what is actually meant here. If we look at how R guesses, or I should say readr guesses what's going on, we can convert this string to raw and guess the encoding when we do that. And the guess is with 46% confidence that it's 8859-1. That's because of the presence of these characters that's making it suspect that encoding. readr can also parse factors and check for errors. So we have a factor, let's see. So we're making apple and banana levels of a factor. And we're parsing this as if it were a factor. And the levels are only these two levels exist. There's a lengthy error message saying that banana was not found in the named set of levels. The main date and time encoding standard is ISO 8601, and this is an ISO 8601 formatted date and time. Time is optional and it defaults to midnight, so we could just put 2010-10-01 and that would be enough. readr can parse dates and times independently, so in addition to parse date time, there's also a parse date and a parse time function, and this is from the library HMS. I don't know, this should be on a separate line, I think. So you can see it parses time correctly. There are also custom encodings. This isn't meant literally, it's help parse underscore date time, help parse underscore date, help parse underscore time. So readr puts it all together. If you guess the parser here, it's guessing date. It's guessing that it's a date in this format. readr tries to match each type in turn. So the first thing it does is checks to see whether something could be interpreted as a Boolean. Then it checks to see if it can be interpreted as an integer, and so on down the list. And if it can't be interpreted as any of these, it's interpreted as a string. Okay, and that's pretty much it for reading. And there isn't too much to say about writing. Writing is really pretty simple in R, um, and you typically don't want to do it. Um, the reason is given right here. Both of these functions which write data lose any encoding data that you've developed in your processing. So what you really would like to do to store intermediate results to disk is to use this library, Feather, which provides a fast binary file format that works across programming languages. So if you're in a situation where you need to save your R data to disk, use that in preference to these. Okay, and then in conclusion, let me just point out that there are lots of ways of importing data into R. All of the bold-faced things here are libraries or programs for importing data into R. So, and then the R data import export manual, actually if you just Google this, actually I just did Google it, and the very first hit for this exact string is the R data import export manual, which gives details on a lot of this stuff plus a lot of other stuff. So there are plenty of resources for reading data in. I also want you to ask me, so when your projects, when you're importing data, you should talk to me about it because I may know just offhand what the best way of importing data is for your project. All right, thanks for your attention. Till next time.